All right, so here is our review for test 2. Just want to go through it here and give you some answers, some ideas, and help you out a bit here. So, all right, so first of all, we got our first topic is probability distributions. Is this a probability distribution here? And the answer is yes, because each of these numbers here are between 0 and 1, and they add up to 1. All right. So those are two things that we need to know about to be a probability distribution. All right, is to find the mean here. Okay. Well, remember this probability distribution means these are the possible outcomes: 0, 1, 2, 3, 4, 5. That's it. And this is the probability that will happen. All right. So to find out on average, the mean is the expected value. All right. So what do we expect if this happens at random? Okay, maybe these are numbers that we can get if we draw them out of a bag or something like that, or number of I'm actually here. It's the number of hits in a game for a player who will be at bat 5 times. Okay, so a baseball player here. All right, or softball. All right, so find the mean. So we're going to multiply x times p of x and add them up. So we're going to multiply and add, multiply and add, multiply and add. You just do that on your calculator and you'll end up with 1.7101. The question also asks us to interpret this. So he can expect, this is the expected value. So he can expect 1.71 hits per game. So the mean is the expected value. All right, the standard deviation. All right, the best formula to use here for standard deviation is mu is the square root of the sum of x squared times p of x minus u squared. So just what you can do is square these. Maybe I'll make a little x squared. 0 times 0 is 0. 1 squared is 1. 2 squared is 4. 3 squared is 9. 4 squared is 16. 5 squared is 25. And then we're going to multiply 0 times p of x, 1 times p of x, 4 times p of x. Kind of like we did with the mean. And then add them up. And we'll find out that the sum of the x squareds, I'm not going to write it all out at the moment here, comes out to be 4.497. Actually, there's a 0 in there. All right. And then we can take that, and now we can go to our calculator, or back to our calculator, because you obviously got that from your calculator. 4.0497 minus, and mu we got up here, 1.7101 squared. Punch that whole thing in your calculator, and you'll get 1.0608. All right, so that's the idea there. All right, so that's the standard deviation. Then we want to find the probability that he will get 3 or more hits per game. All right, so these are the probabilities for each of these. So 3 or more would be adding these up. And so to do that, we just want to go find P3. So 4. We want P3 plus P4 plus P5. Which is, I'll just copy those down, points, oops. So we're just going to add these up here, and we get 0.2229. That's the probability of getting greater than, or of x being greater than or equal to 3. All right. So 5, we want to know the probability, for 132 games, how many games is he likely to get less than 2 hits? So less than 2 hits would be 0 or 1 hits. So we're going to say we want the probability of getting x less than 2. And so that's going to be P0 plus P1, which is, we got 1, 2, 3, 3 plus 0.3206 which is 0.4439. Then we're going to take 0.4439 times 132 games, and we get about 59 games. All right, so that's the idea there. Got to find the probability first, and then multiply it by the total number, and that tells us how many we can expect. All right, number 6, would it be unusual to get 4 or more hits? Okay, so when we're thinking unusual, this means the probability is less than 0.05. All right, 0.05 or 5% is our cutoff. So we got to find the probability of getting 4 or more hits. So 4 or more means these two here, 4 or 5. Okay, so let's see, this is question 6. All right, so we're going to go probability of x being greater than or equal to 4. That's 4 or more. And so that's going to be 0.0450 plus 0.0047, which is equal to 450 and 47 gives us 497. Ooh, that's so close to 0.05, so that's under our 0.05. So yes, it's unusual to get 4 or more hits for this player. All right, that's the idea. And then last question in this group is find the probability that he'll get at least 1 hit. We can do this a couple ways. You can add up all the ones that are, so at least 1 hit. I'm going to mark that, so that would be 1 to 5. Okay, but we know all these add to 1. So really all we need to do is subtract off the 0. So at least 1 hit means 1 minus the probability of getting 0. All right, so probability of at least 1 hit. So we got probability of x being greater than or equal to 1 would be a 1 minus the probability of 0, which is 1 minus 0.1233, which should be equal to, what is that, 88 or 87, 67, I do believe. Okay, so that's the idea. 87% chance that he'll get some hit. So there'll be some games where he doesn't get any hits, but good chance he'll get at least 1. That's the idea. All right. Okay, next group here. So consider the production statistic for questions 8 to 13. The question is, the company produces parts that are within acceptable tolerance. All right. And so to be sold are 91.4% of the time. All right. So they're acceptable. So this is the key here, is that this is binomial. It's a binomial probability distribution. Okay. And the reason is that because it's either acceptable or not acceptable. All right, we can call them good parts and bad parts. Okay, not acceptable. So it's going to be one or the other. It can't be anything else. So that means it's binomial. All right, so we got to kind of cue in on that. Now, we're going to have 10 parts. So that means we have 10 trials. Okay. So in this group of 10, we could have 0, 1, 2, 3, 4, all the way up to 10 possible acceptable parts. All right. So let's make a probability distribution here from 0 to 10. All right. So this is our next group here. So we're going to have x and p of x. All right. And to get this, we're going to use our calculator. And so you can do Binomial Pdf, And this is going to be 10 experiments, and the probability was 0.917, 91.7%. And we're going to put whatever the x value that we're looking for. So we'll put x to be 0, and then hit the second entry key and get 1 and through 2 and so on and so forth. All right. So again, that comes from second distribution is where that's at. Make sure you get binomial distribution, not binomial CDF. See if I can get the right one here. And so we have 10 trials. The probability is 0.917. And then start with 0 and run that. Okay. Just a second here. Get my calculator. Okay. And so we're going to get 1.55 times 10 to the negative 11th. Well, that's 0.000000001. Okay, so that's basically 0. It's a little bit bigger than 0, but so sometimes we put 0 plus, or really it's just 0. And then hitting the second entry key on your calculator, you're going to get 0 again. It's going to be 1.7 times 10 to the 9th. And we're going to continue this all the way through 9. Oh, all the way through 10. So recording it to 4 decimal places, this is what we get here. So we could also go, just write this out to 4 decimal places here. These are all 0. All right, so there's our list, and we're going to use that here for the next couple problems. Okay, so that's 8, 9. We want to find and interpret the mean. Okay, so let's go use these here. Okay, and so the mean, now the mean for a binomial distribution is simply the number of trials times the probability. And so the number of trials is 10 times 0.917. And actually I just realized, I just looked back at the problem, you probably noticed this all along, but it's not 917, it's 914. All right, so the probabilities in the problem was a 914, not 917. Be careful there. I'll keep writing 7. All right. So when you multiply that by 10, we get 9.14. Okay, and so that's the expected value for that. All right. So the most common or the most expected value would be 9. So it just says find and interpret the mean. Okay. So the expected value is 9.17. Okay, in the long run. So expected value means in the long run. You get 9 most often. All right, so next we have the standard deviation. Now actually before we do that, let me go say this is expected value is 9.14 acceptable parts or in the tolerance. Okay. So that we should be a little more specific. Give some units basically. So the standard deviation here for a binomial distribution is on your formula sheet is the square root of n times p minus 1. Or actually, sorry, I got that backwards there. 1 minus p. Because p is smaller than 1. So in this case, we have the square root of 10 times 0.914, and then 1 minus 0.914 gives us 0.086. So if we multiply that up, we get 0.89. And so this tells us 0.89, it's close to 1, all right? So we could say most of the boxes, or the cartons, I think they called it, right, will have about 1, so the average is about 9, okay? We'll have, and so if we go up and down 1, that puts us at about 8 and about 10, okay? So it will have between 8 and 10 acceptable parts. or we can say this is 9 plus or minus 1. All right, so 9 is the expected value of parts, and then we get about 1. So that puts us up to 10 or down to 8. Okay, so something along that line, because we know that about 68% should be between one standard deviation there. All right. Okay, cruising along here. So there's our standard deviation check. There's our mean. Okay, would it be unusual for a carton to contain at least 2 parts that are out of tolerance? Okay, so at least 2 parts that are out of tolerance. All right, so if 2 parts are out of tolerance, we got to interpret this. Okay, so if 2 parts are out of tolerance, then that means there's 8 good or acceptable. Okay, if there's more than 2, then we have, if there's 3, imagine this. So if we have 2 parts that are out of tolerance, then we have 8. If we had 3, because we're talking about at least 2, so we could have 3 bad parts. That means there's 7 good parts. Okay, so these are, I'm just listing the possible number of good parts. All right, we got to think of this kind of in a reverse way. If there's at least 2, if there were 4 bad parts that are out of tolerance, then there'd be 6. You see what's going on here? If there were 5 bad parts, then there's 5 good parts out of 10. If there's 6 bad parts, okay, and you obviously see that we could go all the way down to 0 good parts if they were all bad. So this question is asking, what's the likelihood that we have at least 2 bad parts? In other words, the number of good parts is from 0 to 8. How likely is that? So what we need here is we need to find the probability. Okay. So the probability of X being the good parts. So these are acceptable parts over here. We want X being less than or equal to 8. All right? So that means we need to add up all of these from 8. Now, we can do this with our calculator, Binomial Pdf of 10 parts with the 0.914, not 7, and 8. Okay, so this means 8 or less. 8 or less good parts, which means 2 or more bad parts. Okay, and using our calculator, we get 0.2103. Okay. Now the other way to do this is to take 1, the grand total, and subtract off the probability of 9 and the probability of 10, because those are the 2 outcomes that don't satisfy the requirement, and we'll get the same thing. Okay. All right. And so is it unusual? Unusual means we have less than 5%. Okay, so no, comma, it's not unusual to have 2 or more parts out of that tolerance there. All right, cruising along here, okay? So that's not unusual, all right? So what about if we have 1456, how many would we expect to be free of defects? So we have to think probability first. So free of defects means that we have 10 good parts. All right, so we're talking 10 good parts and 1456 total cartons. All right, so if we have 10 good parts, number 12, okay, so we're going to have 1456. Is that the number? Yep, 1456 times the probability of having 10 good parts. So free of defects means 10 good parts. And so this is 1456. Whoops, sorry. Let's try this again, jump it all over. 1456 times 0.4069. And that's going to give us 592 cartons. All right. So we're interpreting what does free of defects means. Free of defects means probability of 10, okay? 13. What's the probability that we'll have more than one? Well, more than one means we could have 2, 3, 4, or bad. We got 2, 3, bad ones, okay? 2 or more bad ones or out of tolerance. Isn't that what this was up here? So we already found this probability, okay? So we're going to take this probability from up here and multiply it by 1456. All right, so we got this probability here. All right, and so the probability, we're going to 1456 times the probability that we already found. If we didn't find it already, we'd have to go find it. And we get about 306 cartons. Notice, by the way, that we are rounding. There's whole number there because cartons are discrete whole numbers. All right, so now we want a probability distribution here. So there's 40 numbers here. So what we're going to do is we're going to count them up. It's like we have an experiment here. And let's go down here. All right, so we're going to have the numbers are from 1 to 6, right? We're rolling some dice, basically. And so we're going to have x and our probability of x according to that list there. So you might find it useful to go through and just make a frequency list first, okay? So here's 6, we had 6 1s, 8 2s, 9 3s, so on and so forth in that list. The total is 40, so n is 40, so we're going to divide those by 40. And we'll get our values here. You can do them as a fraction, or you can do them as a decimal. Okay. So you could leave them as a fraction, or in fact, some of these, that's 1/10 we know. And this is 1/4, which is 25. And the rest come up to actually be some nice terminating decimals, so their decimals are just fine here. All right, so now I want to make a binomial distribution of 5 trials of using the experimental probability for rolling 3. Okay, so our experimental probability here, the probability of 3 for number 15 here, the probability of 3 is 0.2250. Okay, so now our binomial experiment here is that either you get a 3 or you don't. That's what's now binomial we're talking about. Different situation, okay? So if we have 5 trials, okay, we want to find, so we're going to use Binomial Pdf, 5 trials, 0.225, and then x. All right, so this would be, again, now a binomial distribution. We could get 0, we can get a 3 0 times, 1 times, 2 times, 3 times, 4 times, or 5 times. And then using our calculator, just plug in the number in for x and crank it out. And there's our probabilities. Okay, and that's all we're doing for this problem. All right. So experimental probability was the first one, and then we use one of those probabilities to make a different probability distribution, in this case a binomial distribution. Okay, all right, so next we got a tour statistic of Island Hopper Tours has a 5.6 rate of passengers not showing up. Be careful. We're talking not showing up. Okay, so not showing up here. Let's see. I want to find the probability that 88 spots will have more than 85 people. All right, so that means, let's just list them out. So more than 85. So that's 86, 87, 88 show up. Okay, now we got to translate that into how many did not show up. Okay, so how many did not show up? Well, that means here 0 people did not show up, 1 person did not show up, 2 people did not show up. Okay. All right, so sometimes making these lists here can help you kind of picture the situation, all right? So that these are the different ways that we can have more than 85 people. So this is from 2 down to 0. So we're going to have, for number 16, a binomial CDF of 88 people. And our probability, once again, of not showing up is 5.6.056. And we want to know how likely it is that 2, 1, or 0 will not show up. All right? So using our calculator gives us about 0.1235. All right, 17. So we got 64 spots, and we want everyone to show up. Okay, so everyone to show up. So that means that nobody did not show up. Does that make sense? Okay, so this is the probability of 0. 0 not showing up. So you got to kind of interpret that. Everyone shows up. That means 0 did not show up. 64 spots. All right. So we're going to have 17 here. Binomial CDF. And what do you say? 56 people. Nope, 64. 64 people. Same probability. And the probability that no one does not show up. All right. So go to the calculator. Make sure you change it from the previous one. Now there's 64 people. And that gives us a probability of 0.025. All right. That's the idea. One more. So last one in the group here. Find the probability that we have 76 people. And we'll have from 70 to 75 people show up. Okay. Well, we can do this a couple ways. We could. By the way, we could go find out that this is the probability that they don't show up. If I subtract that from 1, we'll get 94.4%, and you could use that for probability that they will show up. Okay. So you could use that as well there. But let's keep going with the not showing up, all right? So in these cases, what's going on? Well, we got, so we're not doing 76, okay? Or here, let's do this. Let's say it this way, okay? How many people did not show up? Well, if 75, so not show, or we'll call it the no-show. So if 75 people came, 1 person was a no-show. If 74 people came, then 2 people are no-show. All right, so on and so forth. If 70 people come, then there's 5 people. Nope, sorry, 6, because we've got 76 spots. So 6 that are no-show. Okay, so we're talking about the numbers from 6 to 1. So the no-shows from 6 to 1. We need to total that up. Notice we're not talking about 0. There's no 0 on this list. Okay, so this is all the probability of no-shows from 6 down, and then we need to subtract off the probability of 0. Okay, so we're going to have the probability that x is less than or equal to 6, but we're going to subtract the probability of 0. Okay, so the probability of less than 6, that's binomial CDF of, short-term memory here, 76 spots. Okay, 76 spots, 0.056 is the probability, and that's for 6 and down. And we're going to subtract off this number that we already found here, 0.0250. Wait a minute. Got to be careful. Almost made a big mistake. This was 64 people, not 76. So we got to actually recalculate this. Okay? So forget what I just said there. We can't use that. Different number of people now. Just got to recalculate it. So we're going to have binomial CDF of 76 people, 0.056 and 0. And so plug this into the calculator and we get 0.8544. All right. All right. Now, moving on to the last group here, normal distribution here. All right, so now we're going to be using the normal distribution tables here. All right. So here we go. We know we got female patients have a mean glucose level of 157 millimoles per liter and a standard deviation of 23 millimoles per liter. Okay, so find and interpret the z-score for a patient with a glucose level of 118. All right, I'm going to kind of come on over here. Let's do that. Going a bit in circles. 19. All right, so we have 118. So the z-score is going to be 118. Subtract off the mean of 23. Nope, sorry. Numbers right. Subtract off the mean of 157. Divide by standard deviation of 23. And that gives us negative 1.70. Okay, what does that mean? This patient is 1.7 standard deviations below the mean. Okay, that's what that means. Okay, so the z-score tells us how many standard deviations away from the mean we are. Positive above, negative is below. Find the proportion of females that have a glucose level of 125 moles. Okay, so we got to find the z-score. So the z-score for 125 minus the mean 157 divided by 23 gives us negative 1.39. So what we got to do is got to go to our chart. So I'll show you two ways. We'll do the chart way and we'll do it the calculator way. So negative 1.39. All right. We got to find on our standard deviation or standard distribution chart negative 1.3, and then there's, oh nice, this is negative 1.31, 30, 32, can't count, 30, 31, 32, 33, 34, 35, 36, 37, 38, 39, because there's the 9 up there, okay? So that gives us 1.39, and so we get 0.08226 is our number. 0.08226. Okay, so that means 8% of females will have that glucose level. All right, that is the proportion of females. Now, on our calculator, we can use normal CDF. And we're going to go from, we want everything that's below, right, because it says below, right, 0.125, all right, or 125. So below means we're going to do a small number, so negative 1e99. Okay, so a very, very big negative number, we might say, a number that's way to the left, all right? And then we're going to go to 125. And if you just leave it at that, oh, I'm sorry, we want our mu. We've got to enter, because we haven't found, notice we're not entering the z-score. It's going to find our z-score for us. So we need a mu of 157 and a standard deviation of 23. Okay, you've got to tell it that. So if you have the updated calculator version there, then it will kind of find that z-score. I'm sorry, it'll give you the instructions there. Just fill it in. All right, and so that gives us the 0.0. Now this is going to give us 0.08. Whoops, sorry. Okay, 0.08206. All right. Well, which one's right? Well, either one will be acceptable there. This one, using the table, it's rounded off. See, we had to round off 1.39. We cut off some decimals here, so that means it's not as accurate. Here, the calculator is giving us a much more accurate version. So either one would be fine. All right. So 21, we'll just use the calculator from here on now, all right? The females that will have a glucose level above 180, all right? So that means we're going to have our normal CDF. And we're going to go from the low number of 180, from 180 to a giant number. And again, as we talked about in class, you could type like a million there instead of E99 if you want. Just one with a whole bunch of zeros. That's fine. But then we've got to enter the standard deviation in 23. So this is the low. This is the high. This is the mean. And this is the standard deviation. That's what we're entering into our function there. Okay, 0.1587. Okay. 22. All right. Check off my list here. Find the proportion of females that have a glucose between 130 and 190. All right. So in this case, again, the calculator will do all the work for us. All right. So we're going to be between 130 and 190. So our low is 130. Our high is 190. Same mean, same standard deviation. So you can actually just hit second entry on your calculator and just change it to fit that. You might need to, just change it to fit that. And we should get about 0.8041. All right. That's the idea there. 23. Find the number of female doctors you could expect. Okay, so now find the number. All right, so these were proportions, notice, okay? So these were ratios, proportions. Well, in order to find the number here, we're going to have to find the proportion and then translate that into a number. All right, so there's one more step here. So 175, okay, that we expect to have exactly, above 175. So let's find that first, and then we'll talk about the number of patients. All right, so first, the proportion. So 23. Okay, so we got to find the proportion first. Okay, and above 75. So we're going to take our normal CDF, and so above 175 up to a big number. You've got to have something. You got to have some boundary, so we just got to have a gigantic number. Okay, it doesn't have to be that gigantic. It could be, 1 trillion would be big enough. But the bigger, the safer, I guess. All right, and so we have normal CDF, and that's going to give us 0.2169. Leaving that in our calculator, now we have 1860. All right, so that means about 21% of these will fit the criteria. All right, so we want to know the number of patients, and that's going to be 0.2169 times 1860 patients. Now, use your calculator. Hit second answer, actually. Second answer times 1860. Don't retype 0.2169. Use the answer key to bring back a more exact number. Okay, so about 433 patients. That's what we expect. Okay, that's the idea. All right, almost there. Okay, what glucose level would be the 96th percentile? Okay, so now we're going to go backwards. All right, so we want to find the 96th percentile, or 0.96. All right, so we want to know, what ratio would be 0.96. Okay, so we could do that from our from the table. All right, we could find 0.96 here. Find the closest. There's 0.95. There it is, about right there. Okay, and that tells us how many standard deviations. 1.7, 70, 71, 2, 3, 4, 5. You know what? This is closer than this one. Okay, so I would say 5. 1.75. All right, so that's what we're looking at. 1.75. Okay, that's real close to. That's closer than this one. This is, 080 away. This is 0006 away. Okay, so 175 standard deviations. All right, so 2 ways to do this. We could say this means we have 1.75 standard deviations away. So we could take the mean 157 and add on 1.75 of the standard deviations. And that will give us 157 plus 1.75 times 23, 197.25. All right, or we can use inverse norm and tell it we have an area. So we're going to have an area of 0.96. The first number is the area. Then the mean, 157, and then the standard deviation, 23. And that's going to tell us 197.26. So we have 197 patients. Should be at the 96th percentile. I'm sorry, glucose level, not patients. Okay, so the glucose level, what are the units? Let's look at this units. Nanomole per liter. No, millimole per liter is the glucose level. Okay, so that's the units. Millimole per liter. All right. So inverse norm, probably the easiest way to go there. Remember, the percentile is the area, okay? And these pictures will remind you, okay? So the area is the proportion, or we could also say the area is the probability. So we were looking for 0.96. The total area is 1, and 0.96 is the area that we were looking for. Okay, and that translates it for us. All right, what glucose levels would define the middle 90% of the females? Okay, so middle 90%. Okay, so what we got here is we've got think about our normal curve or bell curve here. Okay, and the middle 90%. Okay, so in an area of 0.90 here, there, that means we have it split. So this is 45% on this side and 45% on this side. All right. So what we need to do is this. We need to find the area to the left. Now, first of all, let's see. If we were to find the area all the way up, then this green area all the way up to this marker, this 45% marker, okay, that's going to be our inverse norm. And notice this is, okay, so there's 50% on this side and 50% on the right. So what percentage is from this marker down? Well, that's 95%. 95% of the area is on this side, okay? And this would be 5%. See, half of the area is on this side. 50% minus 45 is 5%. So this little area here is 5%. This little area here is 5%. Okay, so we need to use that inverse norm to find out how many patients, sorry, not how many patients, but what the glucose level is, levels are for down here and then down here. So that'll give us this range. So we're going to subtract up. Okay, so we're going to find this number by taking 90%. We're going to find this number by doing inverse norm of 5%. Okay, so we're going to get kind of a lower and an upper range. Okay, so we're going to do inverse norm. There's a different color here. Inverse norm of 90. 95. Right, 95%. Okay, here's our bell curve again. Whoa, that's ugly. Okay, bell curve, not much better. Okay, so we've got 45% here, 45% here, 5% here, 5% here on my ugly curve. Okay, and so this is 95%. Okay, so 95%, I want to know what this level is here, 157 and 23. All right, and so that's the second entry to bring it back. Let's just do 95. Should be close to our last answer, and that gives us 194.83. Now I've got to find out what this level is here. So the inverse norm of 0.05, that's the 5% level. 5% of the area is to the left of that. And then 157 and 23. Okay, I'm going to make that 05, and that gives us a level of 119.17. All right, so here we have glucose levels between 119.17 and 194.83 we might say will include 90% of patients, or 90% of patients. Maybe a better way to say that would be 90% of the patients will have a glucose level between 119.17 and 194.83. All right, and last but not least, what glucose level would define the top 8%. Okay, so top 8%. So 26. Picture can be helpful. Okay, so if we have 8% up here, what percent do we have down here? Well, that's 92%. So we're just going to do the inverse norm. We want to know if we come 92% up, what will this number be? Okay, so we're going to do inverse norm of 92%, 0.92, 157, and 23. And that gives us 189.32. So 8% of patients will have a glucose level above that number. Millimoles per liter. All right. Okay, there you have it. Okay, so relying on our calculator a lot, but understanding what's going on. All right, so especially on this last group, use a calculator. Be ready to write down what you used to show your work there. All right, and there you have it. Work on it there, and we'll talk more about it, and hopefully it all comes together. Keep working hard. Thanks.